Hi, Dr. Blum again. In this video, we're going to look at Lewis structures that have expanded octets. So as you can see here, my sulfur here has a total of 12 electrons around it. So what dictates if an atom is able to expand its octet beyond 8? So elements in the periodic table that are period 3 start to have a D subshell. So once the D subshell and the F subshell start to get incorporated, these elements can start to expand. So things like sulfur and phosphorus, iodine, any element that has a 3 subshell, so row 3 and greater, are able to expand anywhere up to 12. So you can have between 8 and 12 electrons on these atoms. So we're going to do a few examples. I'm going to remind you of kind of my steps to solving Lewis structures here. So I had basically 4 steps in solving Lewis structures. The first was determining the available valence electrons by adding up all the valence for each atom in my molecule. The second step was to sketch the skeleton of the molecule with the central atom, identifying the central atom as the first listed, atom listed or least electronegative. In the structure. And just remember that hydrogen, even if it's listed first, can never be central. And then we attach with single bonds and that every atom needs at least one single bond, and then we're going to add our lone electrons until all our electrons are used up, and anything left over we're going to put on the central. The third step was to make double and triple bonds to satisfy either deficiency on the central atom, which is not going to be the case here because these are expanded octets, but also to make formal charges as close to 0. And then the last step is always to check that you're using all the electrons that you had to begin with. So check the available. So let's do some examples. The first example I want to look at is SF4, sulfur tetrafluoride. And so for our steps to get the available here for SF4, sulfur is 6 and I have 4 fluorines and each one of those is 7. And so that gives me a total of 34 electrons. The second step is then to sketch it with the central atom being the first one listed first. So we have sulfur here in the middle. And then I'm going to attach each of my 4 fluorines that I have with a single bond. At this point, we're going to now put in our lone electron. So we've used up 8 total with our bonds, our 4 bonds. Each bond has 2 electrons. So how many does that use up? So 34 minus 8 is 26. So I have 26 electrons left to play with. So we're going to make everybody happy on the outside. So fluorine needs 6 more on each one of the fluorines to be happy. And so now that uses a total of 32 electrons. And I have 2 left over, and then I'm going to put those on my central atom. The last thing we're going to do here is check is everybody is happy. So each fluorine effectively sees 8 electrons. And then the sulfur here in the middle has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it has a total of 10 electrons on sulfur. So it's expanded. And that's okay because sulfur is in row 3 or period 3. So we don't need to come and put any double bonds here. Everybody is as happy as it's going to get. And we'll do our check on number 3. We can make sure that we do indeed have all 34 electrons. So the structure without the lone pair on sulfur would be incorrect. You have to have that lone pair there because otherwise you're not using up all my electrons. So we can do, I have 8 on fluorine. I have 8 on this fluorine. 8 times 4 is 32. And then I have 2 more. So that is 34. So everything checks out. Let's do another example. So the next example I want to do is I3 minus. So here we're going to do our steps. The available here is I have 3 iodines. Each iodine has 7 valence shell electrons. And then just to remember, what do we do with that little -1 up there? That means I have 1 extra electron. So that gives me 22 available electrons. We don't really have a choice on central atom here. It has to be iodine, so we have to make our iodines connected. So we have to use up our electrons. Now we're going to work from the outside in. 1, 2, 3, 4, 5, 6. 3, 4, 5, 6. So that uses up how many of my electrons? So now I'm using up 8 on iodine, 8 on this iodine, so that uses up 16. So I have now 6 leftover electrons, and those are going to go on my central. 2, 4, 6. Because this is an ion, I'm going to put my final structure in brackets and then put the charge over the brackets. And let's check our structure at the end. We're going to check. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So I do indeed have 22 electrons and my structure checks out. I'm going to do one more example here of SO2. And again, we know iodine can do this because iodine is all the way in period 5. So this is going to be the last one I'm going to do in this video. This is sulfur dioxide. This always trips people up because there's various ways we can write Lewis structures for this one. And the most common one is usually an expanded structure. So here again, we're going to do available 6 for sulfur and then 2 times 6 for each oxygen. So that gives me a total of 18 available electrons. Sketch it. Sulfur will be central. We'll work this from the outside in. So I have 2, 4, 5, 6. 2, 3, 4, 5, 6. That uses up 16 total electrons, and I have 2 more left. First, we have to see that sulfur is not happy at this stage. So we first have to make sulfur happy. In order to make it happy, we're going to take one of the lone pairs away from this oxygen here and then create a double bond. Now if we look at this Lewis structure, this Lewis structure is complete. Everybody has 8. Nothing is expanded here, and you think, well, I should be done. But when we calculate formal charge, and the formal charge is calculated at each atom, it's the number of valence electrons for the atom minus the number of bonds and minus the number of lone electrons. So if we do this calculation, I'll just call this oxygen A, this oxygen B, and then the sulfur is clear. So if we do this calculation for oxygen A, we get oxygen has 6 valence, it has 2 bonds, and then 4 lone electrons, and the formal charge of this is 0. If we look at oxygen B, B has still oxygen, 6 valence, 1 bond, and then it has 6 lone electrons, and it has a -1 formal charge. And then we can look at sulfur. Sulfur also has 6 valence. In this picture, as I have it drawn, it has 3 bonds, 2 lone pairs, and it has a +1 formal charge. So if I go put my formal charges on my structure, then I have a sulfur with a +1 formal charge, and my oxygen here with a -1 formal charge. Molecules are the most stable when the formal charges are 0, or if there is a negative formal charge, that the negative formal charge is on the most electronegative atom. Well, that holds for oxygen, because oxygen is significantly the most electronegative atom in the structure, but sulfur has the capability of expanding. And because sulfur can expand, it can take these 2 electrons from oxygen and again make another double bond. So it will move those electrons over, make another double bond, can erase this lone pair of electrons here. And now when I did that, the formal charge on sulfur, the new formal charge on sulfur, is 6 minus 4 minus 2 is now 0. And then the new formal charge on oxygen is also 0. So now the formal charge for all the atoms in my modified structure is 0. This can be done because, again, sulfur can expand. Because now in my new picture, sulfur has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons on the central atom. But that's okay. So this is the Lewis structure that you will find most commonly drawn for sulfur dioxide. Alright, I hope that helps everybody out, and happy drawing Lewis structures. Thank you.